So hi everybody. I want to talk about something kind of, it's related to GPU, but it's been going on, our community at large has mostly been focused on graphics for a long time. Compute is becoming much more and more something that is more pervasive inside the whole computing industry. And so I want to talk about heterogeneous computing and stuff like that. And I wanted to start with something kind of small, and that's why I actually focus on get you the page, because it's something we all actually do use today inside many of the upstream GPU driver inside the kernel. So for the people that don't know, GUP, it's the acronym for get user page. It's a set of several functions inside the kernel that allow you to get the page that is backing a virtual address, but I will go into more details during the presentation. So I think the first thing I really want to say is like heterogeneous computing is kind of becoming a real thing, and you see GPUs being used much more massively across the industry in a way that were not did exist in last 10 years. NVIDIA has been pushing with CUDA for a long time for compute, and we also had OpenCL, even if OpenCL never really take off in any meaningful way, at least from my point of view. So nowadays, with all the AI stuff, you see a lot more use for GPU, and I'm going to ignore all the mining stuff, the coin mining and cryptocurrency stuff. It's really kind of a weird phenomenon. And you not only have GPUs, you also have much more bunch of accelerators that are actually popping up inside SoC and inside even outside phone. Actually, on platform, you will see Intel and AMD are pushing more stuff alongside of the CPU core. You will get a bunch of small cores being able to do a bunch of things like cryptography, encryption, compression, and accelerate some of the workload that have been so far done on the CPU, but have been a kind of a drain from a power point of view. And you also have FPGA. It's kind of a thing on its own, but it's also much more of a niche, but still something that do exist inside people's heterogeneous field. And the bottom line really is that the CPU is no longer the only stop in town. Basically, many people know they develop their program around the assumptions that they're going to use CPU and GPU or FPGA or something else, or it can be a combination of everything. And the outcome of that is that the system topology is also becoming much more complex than it used to be. With NUMA, so when you have multiple sockets, CPU sockets, you used to have multiple nodes and multiple servers that can be interconnected with each other. And it was creating a topology of memory. What is your local memory? What is the memory that is kind of far away from your CPU cores and stuff like that? It was already complex, but if you add on top of that, if you add the GPU, FPGA, and whatnot, and each of them with their own memory topology, it really get the whole picture gets even much more complex than it used to be. And to top it off, really, we have seen the advance of new memory technology, like HBM, which is stacked memory on top of your die. So you can have HBM for GPU, but you can also have HBM for CPU. So HBM is a small chunk of memory. By small, it's a few gigabytes, but it's still compared or perceived as small compared to the rest of the memory. HBM property is that it's much faster than your main memory. You have a greater bandwidth and a smaller latency. So ideally, you want every data that you often access, often read, or often write, you want it to be inside HBM. So it doesn't only apply to CPU, it also applies to GPU. You have obviously your usual main memory, DDR memory, and you can have also persistent memory, which is slightly slower, but also much bigger. You can have a persistent memory in a terabyte range easily. So talking about topology, I just wanted to give a small example of how it might look So you can have multiple CPU, so it's kind of a socket. It kind of depends on you know which architecture you're talking. If you're talking about PowerPC or if you're talking with Intel, AMD, or ARM, they each have their own lingo and they each have their own differentiation between what is a socket, what is a node, what is a CPU. So you can have a multiple CPU node. Each of the CPU node has the main memory and also can have a HBM memory. So trying to give typical figures for the bandwidth, the DDR memory usually with DDR4 is around 64 gigabytes per second. HBM memory on CPU usually you see I think 512. You know, it's often upward of 2, but not exactly. So 512 gigabytes per second, almost a factor 10. Then you have your GPU, and most of the time they're connected to something like PCI Express and PCI Express 4. If 60 lane, you're gonna reach 64 gigabytes. Yeah, I think it's at 64 gigabytes per second of bandwidth. But the latency is also kind of crappy on PCI Express. And the GPU memory today, ION GPU is around 800 gigabytes per second of bandwidth. Some are reaching 1 terabyte, I think. And so on top of that, so this is just one node, and on top of that you can have multiple nodes, and each of them can replicate the same schematic. So if you have the node 1 is also connected to the node 0, and there is an interconnect. Usually it's the same speed as the memory or slightly slower. And on top of that, now you have what is called GPU interconnect. So it can be I don't think AMD has a marketing name for it yet. We have XWGMI or something like that. NVIDIA have NVLink for that as a marketing name. And it's a fast interconnect that allows GPU to exchange data much faster than if it were to go through PCI Express. So if you are able to spread the workload you're working on across multiple GPU, and they have this kind of interconnect, you can really take advantage of the bandwidth it's offering. So with that kind of thing, the problem now becomes that you want to maximize the performance of your computing. You want everything to be as close as possible to the unit that is actually doing useful work on the data. So, you know, if your CPU is crunching number, you want the input data set, and also the output buffer to be on the device memory as much as possible. And then you have a bunch of constraints that actually can impede you from actually achieving that. So, for instance, the GPU memory size might not be big enough to hold the whole data set, or you can have also the data set that is used concurrently by multiple things. So you can have the same data set that is used by the CPU and GPU at the same time concurrently, because, you know, the GPU might be working on one aspect of the data set, and the GPU might be working on another kind of aspect on the same data set. And also you obviously have other things that come into play, lifetime, and how the sysadmin want to manage resources on your system and things like that. So what I'm trying to picture here is it's like the picture of the computing system is becoming much more harder and much complex really to manage. And to avoid to add even more complexity on top of that already complex things, you want to keep business as usual as much as possible from the application point of view. You want to allow library to use this new kind of memory as if it was the old regular memory they used to, so we don't have to learn new tricks. You don't want to teach these old monkeys new tricks, basically. And you cannot also allow any of expectation from application might have and reliance they might have on the memory model of your platform. So, you know, x86 or ARM, they have a different memory model for concurrent access and how Atomix works and things like that. Same for PowerPC. So you really want to keep that kind of thing the same, whether it's going through the main memory or whether it's going through a device memory. One of the issues for that is not all the interconnect you have on platform nowadays are equal in that sense. for instance, on PCI Express, you cannot allow the CPU to access device memory because the PCI Express specification say that any atomic access to device memory is actually undefined. What happened is undefined. And depending on your platform and depending on which Intel version you have or AMD platform you have, what happened really is like up to whoever best guess, like whatever you guess is, I have no idea. So that's why you have seen in the last couple of years new bus like CAPI on PowerPC, which is an extension to PCI Express that does allow CPU to do current access to device memory, and also CCI-X, which is more ARM and AMD. So same aim really is to allow CPU to access device memory in a cache current way, so that atomic access by the CPU is actually defined, and you get what you expect from it. And it doesn't mean that because PCI Express is, is still so pervasive, it's still the main system bus you're going to find on everybody's platform. It doesn't mean that you cannot do what I want to talk about on PCI Express. There is actually a way to do it on PCI Express, and that's one of the things I will go in further detail during my talk. And so, like I say, you don't want to complexify the picture for the application to be able to use that. So the first thing is you don't want a split address space. You don't want to have one address space for your CPU and one address space for every single of your devices. Because a different address space means that pointers value don't mean the same thing whether you are on your CPU or you are on the GPU. Right now, from a graphic point of view, most of the graphic pipeline is designed around gem object and things like that. Which is don't necessarily expose GPU address to the user space. It also kind of depends on which driver you're talking to. So, there's differences between AMD and how AMD implement virtual address and how Nouveau implement virtual address on GPU and things like that. Same for Intel. There is also the graphic pipeline is very much around the design around the ideas that the application knows when to move that around, so it knows how to explicitly do copy between the two, between the main memory and the GPU memory. That's what games have been doing for a while, and now we are pretty good at doing that and pretty good at optimizing for this aspect. One of the big issues if you have split address space is really, if it's a flat object, if it's a matrix or an image, it's fine, it's not hard. But if you have some kind of complex data structure like a tree or a double linked list or a list, so a single list, it's becoming really cumbersome, because it does mean that for every pointer you have on your CPU, you will need a new pointer for every single device you have. So if you have one GPU, you will need an extra pointer for the first GPU, and if you have a second GPU, you will need an extra pointer for a second GPU, and so on and so forth. And obviously keeping everything in sync when you add a new element to a list, or when you remove an element to a list, or when you add something to a tree, or you remove something from a tree, it's becoming really complex and hard to maintain. And beside that, it also kind of breaks the programming language system and memory model. So, if you look at the C standard specification or the C++ standard specification, they define a model of the system, how the system is supposed to behave, and we also define a memory model since C11, for instance. So the split address space is kind of an easy thing to fix, actually, easy things to solve. It's all virtual address, so what you really want, basically, is that the same virtual address to point to the same physical memory. Kind of obvious, really, so it's not really hard. And if you do that, then your GPU can use the exact same pointer, and if you did everything right, then whenever your GPU reference a pointer, it will actually go look at the same memory as your CPU would have looked at if it was looking at the same pointer. So it makes all the complex data structure work out of the box. You don't have to do anything. If it works on your CPU, you're going to work on your device, so nothing to do there. The downside here is that you don't have explicit copy anymore. You don't expect your application to do, okay, this this bunch of memory should really be on the device memory, so you don't have this explicit expectation from the application. The other nice aspect is that it does preserve the programming language system and memory model I was just talking about. So, and one of the holy grail for many of people working on GPU compute is being able to offload transparently part of an application on the GPU or on a device. And they work on the compiler to be clever enough to understand, to find pattern inside the programs that can be offloaded easily. It's kind of an holy grail. I don't know if we will ever reach something that is really meaningful and really achieve something interesting here. So I want to work through a small example. It's basically a double linked list. So on the top, you have how it looks if you have a split address space. So now you have your usual previous and next pointer for the CPU. But if you are in a split address space scenario, you need to have a pointer for the GPU. So you have the GPU pref field and you have the GPU next field. And it does mean that whenever you add an element or you remove an element, you need to also update these two new fields. And it's just for one CPU. And you can guess that if you add more device, you have to add more pointers. And so it really becomes quickly ugly and quickly unmanageable, really. And obviously, when you just have the same address space, then your usual data structure stays the same, and your function stays the same, and it all works as you expect, and you don't have to modify anything, really. Just works, basically. So I think it really shows how a split address space is not something you want to keep around. So obviously, people have been really enticed by this idea of having the same address space, and the first idea most driver have is, well, let's use get user page, because get user page is look up a virtual address and give me the page of physical memories that is behind a virtual address. That's what GUP does. And so people assume, the vast driver did assume that, well, this is the tools I want to use. Except it's not exactly that. GUP was originally done for direct I/O. I'm pretty sure that's the original use case. I didn't do any archaeology on that because it predated 2.16 and it goes beyond the Git history. So I'm pretty sure anybody that will do any archaeology on that will agree on that. So, but the thing is, driver do have this kind of often when I talk with the device driver, they have kind of this expectation about GUP being kind of a magic thing that does everything for you. So they assume that when you do GUP on a virtual address, you're going to pin the page so that the association between the virtual address and the physical memory will stay the same forever, which is not the case, really. So, yeah, and they assume that it's going to protect them from anything bad happening, basically for anything that usually happens inside memory management to happen, so that they can keep working. They can keep assuming that once we have done a GUP, we're going to be able to work on the same memory as a CPU. Except it's really not doing that. For real, what GUP does is it just finds the physical memory that is backing a virtual address at an instant, at some point in the timeline. And beside that, there is absolutely no guarantee. So, for instance, it does mean that by the time you do a GUP, and by the time the GUP function returns, the page it just returns to you when you call it might actually not be the page that is backing the virtual address anymore, because something might have happened inside the subsystem concurrently. And by the time the GUP returned, it already modified the CPU page table to point the same virtual address to a new page. GUP doesn't protect you from things like fork. People love to fork, truncate, and many of the POSIX syscall that does exist and are kind of pervasive and see a lot of use on Unix. And obviously, gup doesn't synchronize with any CPU page table update. So it means that once you have done a gup, after the gup happened, at any point in time, the virtual address might point to a new page, and you will never know about it, and the device driver will never know about it. So what it means really that gup is not the tools you want to use. If you want to have the same virtual address point to the same memory on both your CPU and GPU. And that's where HMM, which is the heterogeneous memory management things, come in. So HMM is it's kind of a toolbox, really. I wanted to make it a one-stop for all the MM needs from a driver point of view. So I want just to talk about some of the main tools you have inside that toolbox. You have much more, but some of the main tools is a bunch of helpers that does allow you to mirror the same program address space onto a device, which basically means mirror the CPU page table inside the GPU page table. It also has helpers to keep the two page table in sync, so always synchronize with each other at any point in time. So making sure that at any point in time, the same virtual address will point to the same physical memory on both the CPU and GPU, so that at any point in time, we will both see the same thing. And one of the other things is also to be able to use device memory. Because like I said at the beginning, device memory has a pretty big bandwidth compared to main memory, and it's much better than going to the PCI Express bus. And one of the other things, I think it's kind of hard to understand, but that was one of the motivation too, is I want to isolate as much as possible the driver from the MM changes. You know, when MM change, and there is a lot of churn actually happening to MM, much more than you will actually guess or think or believe. And a lot of the change are subtle and finally change something in the MM, and some of the assumptions you might have had in the past no longer holds. So the idea is that HMM is kind of a buffer, an impedance layer, if you wish, that allow you to avoid having to constantly monitor what is happening inside the MM, and just like HMM provide you an API, and there is a contract with you and HMM that this is the API you're going to follow, and then the contract is that whenever something happens to MM, the HMM will be updated so that it keeps working. And the reverse is also true. Like HMM is also a way to isolate the MM folks from the device driver, so whenever the MM folks want to update the MM code in any way, they don't have to go chase down every single device driver inside the Linux kernel tree and find how to modify every single device driver, so that they suddenly have to understand many device driver code that we don't really want to learn about. So this is really something I think that matters in the long term. You know, it's kind of a relative thing. In one way, you can say, well, this is to isolate the glorious MM folks from the pesky device driver people, and the reverse is true. You know, it's to isolate the glorious driver people from the pesky MM folks. Basically, it's like it's kind of a fence, so that you can each other can talk over the fence, and you know exactly where the boundary is and what is the boundary and what you can and cannot do. And you know, it's really kind of a relative perspective for each other. So to mirror the address space, you have multiple solutions. You have the hardware solution. So on PCI Express, you have something called address translation services and process address space ID. So the idea is that every process on your CPU gets a unique ID, and unique ID is tied to the CPU page table, and the I/O menu on your platform can use that process ID to look up for every virtual address, to look up what is the physical memory behind the virtual address on the behalf of a device. So this is the translation service provided by the I/O menu. So it's something that has been on PCI Express since I think PCI Express 4 or 3. I don't remember if it's mandatory. I think it's not mandatory. It's probably an add-on to PCI Express. You don't necessarily have to have that. You have CAPI, things like, so CAPI is for PowerPC. It's cache coherent, so it not only provides you something like ATS and PCIE, it also supports device memory, meaning that the CPU can access device memory and be cache coherent. And what happens when the CPU accesses device memory is actually well defined. You also have CCIX, exactly the same thing really. It's again ATS, PCIE, and also support device memory. And you have the software solution, which is HBIND in that case, that allow you to transparently use the GPU memory, device memory, over PCI Express. So even if you don't have a CCIX or CAPI, you can still use device memory thanks to a software solution. Yeah, so just want to get the point across. You really don't want to give up on device memory. Like on GPU, you're talking about 800 or 1 terabyte of bandwidth versus the 32 or 64 gigabyte of PCI Express 4 or 5. So, you know, it's 20 times faster if you use local memory, and latency is also much better. And if you ever look at PCI Express Atomic, how it works, it's really awful. You can only do 64-bit or 32-bit atomic operation, and they are like wasting bandwidth. It's really awful. And besides, when you have to go through the main memory, you also have to go through many layers. So you have your GPU that's going to throw to its and then going to throw over the PCI Express that will reach the IOMMU. The IOMMU will go to the physical memory, and you can have multiple stops actually in between every one of them. So it can really slow you down and add the latency to everything you do. So the issue here is that the PCI Express had been designed a long time ago and was designed really as a kind of as a sink where the CPU was dumping data over a PCI Express bus and the data was set on the device memory, and then the CPU forgot about it, wasn't trying really to access it in any meaningful way. You know, it was not about sharing data, it was more about, hey, this is a bunch of data, you can use that, and I'm going to work on my own stuff. You have also a bunch of small issues that are kind of no longer really a big issue. The PCI Express bar, which is a window inside the device memory, it used to be a fixed size of 256 megabytes. Obviously, when you have several gigabytes of memory on your GPU, it does mean that you don't have windows that allow you to access the whole memory of the GPU. But it's been fixed, mostly on all platforms, I believe. And also, PCI Express is being a protocol thing, it kind of adds up on latency. One other thing you need to understand is that there is so much that can be done in software, so there's still a bunch of requirements from the hardware perspective. You cannot do anything you want. So HMM does require you to have a GPU that does support page fault, basically, because you don't want to always have physical memory behind every virtual address of your program. That's one of the big things in every application, is that you do memory overcommit all the time. The Linux kernel never really allocate all the memory, so when you do top on your program and you see the memory consumption is actually virtual address consumption, it's not actual memory. And you also need to be able to update your GPU page table in a way that allows you to synchronize the two. So either you allow update to be asynchronous, or you have a way to quickly and easily update the GPU page table by, for instance, preempting whatever is running on the GPU, so that you know that you can stop the GPU, update the GPU page table, and resume whatever the GPU was doing. Small details. You also want to have the GPU that supports the same number of bits for every virtual address. So on x86 64, up to recently, up to I think it's Skylake or Cannon Lake, I guess. It's 48 bits of virtual address. That means when you have a 64-bit pointer, there is only 48 bits inside that 64-bit pointers are actually meaningful for the virtual address. And with the last generation of Intel and I think AMD2, you have what we call 5-level page table, which give you 57 bits of virtual address. Starting to become big enough. Well, let's hope. And one thing also that sometimes people don't get is that when you use HMM, like I say, it's a toolbox, so you don't have to use all the tools in the box. You can use only the tools you want. And so you can mix and match existing hardware solution like ATS PSID with HMM and only use the tools you really want to have. When you do HMM on top of PCI Express, there is one thing you cannot do. You cannot pin the memory to the device memory. That's not something you can do because we need to be able to evict at any point in time the memory back to main memory so that CPU can access it. Because when the memory is inside the device memory, actually, we cannot allow CPU to access the memory. So yeah, so like I say, it's really a toolbox. Bunch of helpers and bunch of things to help you achieve everything. I won't go much into that. Quickly how it works. So one side is about mirroring having the same address space on the CPU and on the GPU. So the thing is you want to synchronize the CPU page table with the GPU page table. And for that we use the what is called the unifier inside the Linux kernel. It's something that the Linux kernel calls every time it's going to modify the CPU page table. So every time the CPU page table is about to be updated, you have these calls back, and then you say, well, let's actually either stop the GPU or invalidate the GPU page table and wait for the CPU page table update to be completed before I update again the GPU page table. So HMM provides a bunch of helpers that allow you to do that and kind of isolate the device driver from all the gory details of MM and MM unifier. To expose the device memory, so one of the key data structure inside the Linux kernel is a strict page. Strict page is you have one structure for every page in your system. Most of the time the page size is 4 kilobytes. And that's a structure that the Linux kernel is using pervasively across the kernel to reference memory, really. When you do a translation from a virtual address to a physical address, what you get is usually a strict page, really. So that's what you really that's what the kernel expects to have whenever you want to get a translation from a virtual address to a physical memory. So for that reason, HMM is just doing exactly the same thing. We just outplug, add new strict page for the device memory, and that's what get used by the kernel. So you don't have to modify anything in the kernel. From the kernel point of view, it's business as usual. Like I say, you cannot access the device memory from CPU on PCI Express. So when you migrate your data set to the GPU memory, you actually update the CPU page table, and you make it look like the data is actually swapped out to disk, exactly as if it was swapped out to disk, but it's not. So it does mean that if the CPU tries to access it, it will fault, and comes to you, and so you will be able to do a migration back to main memory. So just really for explaining how it works, kind of. And the last aspect here, so now you have the same address space on your device. You can use your device memory inside your program, but how do you use your device memory inside your program, right? You have to find a way to migrate memory, to copy memory over from main memory to device memory. And there's like really two ways that can happen. There is some kind of automatic placement where you have some kind of daemon that monitor your program and look at what device is accessing what, and try to migrate memory to the best place at all time. And in the kernel, you have AutoNuma that is doing just that, but it's not really tailored to handle the device case. And you have the explicit memory placement that has been the one thing that has been always used on the graphics side, really, where you have explicit control by the application on where things are. So this is the two things you can do, really, for memory placement. And they both come with baggage, basically. So the challenge with automatic placement is how do you know where to place what, and how you figure that out. So it means you need to monitor the program access pattern to some way. Either your hardware is clever enough to provide you introspection register or some kind of thing that can allow you to monitor sniff what is going on the bus. And the cost of monitoring and handling the data. So, when you monitor something, you are collecting data, so you need to store that data so you can actually have statistics and meaningful statistics. So that have a cost, not only memory cost, but also a CPU cycle cost. And then you have like all this conundrum, when you don't want to over-migrate stuff, so you don't want to constantly migrate things because, okay, the CPU just accessed that, let's move it back to the CPU memory, and then like 1 millisecond after that, the GPU is accessing the thing again, and you migrate again to the GPU, and 1 millisecond after that, the CPU accesses it again, and that's so that you can ping-pong between CPU, GPU, and so on and so forth. So you don't want to be too aggressive on when you do migration, or you don't want to be too slow either, So if you say, well, let's wait before I do this migration to the device memory, and by the time you actually decide to do the migration, actually the device might be done with this computation, so you're just going to do a mem copy for nothing. And then you have things like competitive device access. So when you have multiple devices that want to access the same memory, or multiple CPU and device that want to access the same memory. On top of that, you have the topology to think of. So, if you have multiple node or multiple GPU and how they are connected to each other, how they can talk to each other, and so on and so forth. So the last thing is really explicit memory placement, where you give the application the control over where to place what and how to do it. In many cases, the application knows best really what's going to happen because the application, is designed to compute something, and the application can have beforehand knowledge about how things could happen. And when that does, then the application can really decide what is the best memory placement for everything. The big advantage is that you don't need to do any monitoring, and but the drawback is that the programmer needs to actually think ahead of time about that. And in some cases, actually, programmer, even if they know their program well, in some cases they cannot actually guess what's going to be the memory access program of the program. So in some cases, we cannot rely on that, which is why you have to. You have to kind of have the two solutions, really. So, yeah, I'm going to finish with that. So, that's why I'm pushing a new. So, for those of you that are familiar with NUMA, there is something that is called HBIND. It's a syscall that does allow you to bind memory to a specific node, a NUMA node. So it's well defined for NUMA and very CPU centric. It serves us well for everything dealing with NUMA. But for heterogeneous memory, when you have device memory and things like that, it's really it's not up to the task really. So HBIND is a new syscall for doing just that, basically. Where you can select device, you can select device memory, you can select CPU memory, you can select any memory inside a complex topology, really. So it's a new syscall to help you just achieve that. And really, that's pretty much it, really. Obviously, there's always a question that's left to be answered. So, with no further ado, if you have any question about any of that.
Are there any questions? No questions? Then, okay. So, thank you so much for your presentation.